This example is about kinematics and unit conversion. Pretty much any kinematics problem is going to come down to this equation. This tells me if I want to know where I am, I need to know where I was, how fast I was going and for how long, how much I was accelerating and for how long. And based on that information, I can figure out where I am. Often you're concerned with a change in position, delta x, and a delta, or triangle, hides inside of it final minus initial. So if I want delta x, that's x final minus x initial. If someone asks you for delta v, that's v final minus v initial. And this x up here is really my final, so where I am, where I was. So this equation can easily be changed to a delta x by just moving over x naught. Then you'd have xf minus x initial, which is delta x. So this equation easily becomes delta x equals v naught t plus 1/2 at squared. And the limit of this equation is that it only works for constant acceleration. In fact, that's what kinematics in general is. Kinematics is constant acceleration problems. So we have to have the requirement that the derivative of acceleration with respect to time is 0. Let's consider an example. Suppose we have a car that starts out with an initial velocity of 47 kilometers per hour and speeds up to 57 kilometers per hour in 2 seconds. What if I want to know what is the acceleration during that time? And remember, it's constant, so over that 2 seconds, the a at any time will be the same answer. And I want to know how far I went in that 2 seconds. How would I go about this? Well, I need to know both my initial velocity, check, and my acceleration to use this equation. But as the problem suggests, I don't know acceleration, so how can I figure that out? Well, acceleration is just the change in velocity over the change in time. So if I had an equation for velocity in terms of time, I could take the derivative and get my acceleration. If I just have a discrete set of points, so calculus doesn't help me out a lot, and by discrete set of points I mean just 2 particular or any number of particular places. So I have 2 particular velocities, so I can change this equation for that case. Change in velocity, which remember that delta just hides final and initial, over change in time. And this we know. We have our final, we have our initial, we have our time. So let's try this. A equals delta v over delta t. And if I just look at these numbers, 57, 47, the change in velocity was 10 kilometers per hour. And my change in time was 2 seconds. Now, notice that my units for time aren't matching, and so I need to fix that. And you're probably used to, in general, seeing acceleration as meters per second squared. So let's go ahead and take this opportunity to do some unit conversions. Let's change 10 kilometers per hour, or delta v, into meters per second. So I want to take delta v equals 10 kilometers per hour, and I want to get it to meters per second. Hopefully you've done this in either a high school physics or high school chemistry class. Dimensional analysis is in general the realm of a high school physics or a high school chemistry teacher, and I say that as someone who taught high school physics. So let's do this real fast. 10 kilometers per hour. I need to get rid of kilometers and replace it with meters, and get rid of hours and replace it with seconds. Dimensionally, I do that by setting up a fraction that is equal to 1, but changes the units. So I need to get rid of kilometers. Okay? So if I had a fraction with kilometers on the bottom and multiplied it by kilometers here, that would eliminate kilometers. Well, what am I going for? Meters. How many meters are in a kilometer? 1,000. So this fraction is equal to 1 because 1,000 meters divided by 1 kilometer is 1, so I haven't changed anything. And then those units cancel. But I still have the problem of this hours. So I need to get rid of hours. The way to do that is to have a fraction with hour on the top, and I'll just put a 1 there because my fraction is going to be equal to 1. And there are 3,600 seconds in an hour. And you can check that real fast. 60 minutes, 60 seconds, 3,600 seconds. And then the hour will cancel. And when I do this out, I'll have meters over seconds. When I do this, I get that our delta V was 2.8 meters per second. And now I can find my acceleration in meters per second squared. So A equals, and just taking this 10 kilometers, we know is the same as, 10 kilometers per hour is 2.8 meters per second. 2.8 meters per second over 2 seconds equals 1.4 meters per second squared. I also want to answer the question, how far did I go during that time? And I'll refer back to the equation I wrote up here. T plus 1/2 AT squared. So I have V naught, but it's in kilometers per hour. So we just need to do this conversion real fast. I'll do it off to the side. 47 kilometers per hour. This is initial velocity. Times, and notice it's the same thing, because I need to cancel kilometers. Hour, 3,600 seconds. I need to cancel hours. And when I do that, I get 13.06 meters per second. I'm being a little sloppy with my significant digits. This should really just be 13. So we could write down if we wanted 13 meters per second to make it easy. And the reason it should be 13 is there were only 2 known digits in my original velocity. Right? So now I have enough information to fill in this equation. This becomes 13 meters per second times 2 seconds plus 1/2 0.4 meters per second squared, 2 seconds squared. And when I do this out, I get 28.8 meters. If you'd kept that 0.6, this would have turned this into 28.9, the only difference that might happen. So that is my change in position. Let's do this again just so you can see the power of some of these equations. So one more time. This time let's have a car that starts from 81 kilometers per hour and goes to 91 kilometers per hour, a time of 2 seconds. Well, right away, I notice that my delta V is still 10. And we already found earlier, if I look back, that delta V of 10 kilometers per second, or 10 kilometers per hour, in a time of 2 seconds, ends up being 1.4 meters per second squared. So it's the same acceleration. And note that the acceleration is dependent on the change in these two velocities, not just the velocities independent of each other. The change in the velocities and the time determine the acceleration. That's careful here, over 2 seconds equals 1.4 meters per second squared. All right, and now I could answer the same question of finding my change in position. But I have a different V naught of 81 kilometers per hour. Why don't you take a second and go ahead, work through the dimensional analysis to change this into meters per second, and see if you get the same thing I do. When I do that same dimensional analysis, multiplying by 1,000 meters per kilometer, 1 hour, 3,600 seconds, I get 22.5 meters per second. And my delta x, 22.5 meters per second for my V naught, 2 seconds for my time, half the same acceleration as last time, time squared. I get a delta x of 47.8